Okay, so before we begin, to Sid and Brandon and the judges and Megan, thank you guys all for being here. We're really, really excited. So, hello and welcome to the Cyclist Visibility Team's Demo Day presentation. We're also known as Team 16. My name is Brooke Zivotofsky. In this project, I worked alongside Jordan Gottlieb, Marlena Gutman, and Katie Oppenheim, all of whom are systems engineers like me. We've taken classes together for the past 4 years and wanted nothing more than to work together on our senior design project. We have been working under Megan Ryerson, who's not only a graduate of the systems engineering program, but is also a professor in the engineering department, as well as in the Department of City Planning. So what does our project do? Well, our project creates a methodology to assess and quantify the visibility of helmets, specifically high-tech helmets such as the Lumos helmets, which we'll get into a little later. Mainly, our project focuses on how do we quantify the safety of a bike rider based on the inputs of their helmet. So let's go to the next page. So the first thing that's important to talk about is why we even went about this project. Why did we see that this needed to be fixed? Well, the first thing that I want to draw your attention to is the picture on the right, which is a heat map of where crashes happen in the greater Philadelphia area for bicycle riders. As you can see, a lot of crashes happen. We absolutely want to avoid that. As you know, in the pandemic, when people were trying to avoid public transportation, and as people become more eco-friendly minded and health minded as well, people are riding bicycles more. And we want to ensure that when you get on that bike, you are absolutely safe. Well, unfortunately, the current measures of safety are very retroactive and limited. What does retroactive mean specifically? It means that we are measuring safety after the point at which someone has already been hurt. These safety calculations and qualifications are informing how governments and city planners spend their budgets, how people plan and design cities, etc. We no longer want to take this retroactive approach, and that's where our team comes in. So what's unique about our approach? Well, first of all, it's proactive. It comes in before anyone ever gets hurt. It also takes on the perspective of the roadway user. I'll get into kind of the past research on this topic, but you'll see that not much is based on the real true data of what people are seeing when they're driving their cars or they're riding their bicycles. 3, it's based on eye tracking technology. We'll get into that yet again, but we're really focusing on pupil movements and where people and roadway users are looking when they're riding their bicycles, walking on the street, or driving their cars. And lastly, and this is what I really want to drive home, is that what makes our solution unique is it creates a framework to move the needle on the research that is happening in this field. Currently, like I said, the research is extremely limited and not really helpful to anyone. People are not becoming safer as a result of the research. And we truly believe that our approach is unique enough and new enough that it's going to kind of create a new field and a new way in which we study safety. So before we get into more on our project specifically, I want to tell you what we're working with and what other research is out in the field. So one main number that is people really hone in on is KSI data. So KSI data is called killing or seriously injured data. So like I said before, retroactive, comes in after someone has ever been hurt. It's also not always as accurate as possible because, people are already avoiding the more congested streets, which is driving down numbers. The other way that we're currently measuring safety is in a simulation. So, for example, a driver in a simulation stops at a stop sign. Well, as we know, many people drive right on past stop signs. And so by doing our project, we avoid those kind of mistakes or things that you could miss in a simulation. So I'll pass it on to Marlena to talk more about the company that we've actually been working with.
Hello. So we are working with a company called Lumos. We were introduced to them through Dr. Ryerson. They're a high-tech helmet company that creates helmets with special features, such as LED lights and blinkers, And the goal of this helmet company is to help advance cyclist visibility and safety. So, in our project, we're sort of using their products to gauge the gap between this next generation of helmets with these special features and the status quo. So, your typical helmet that you see on the street. So, we looked at two different helmet styles, the Matrix and the Kickstart, as pictured on the right. As you can see, these have different light patterns and are priced differently, which has different implications for visibility and safety. And hopefully, with this data, we can make conclusions about how this new technology can impact safety and hopefully impact policy and even consumer decisions. So, in our project, we used several different methods of technology to sort of take measurements of safety. First off, we used Tobii eyeglasses. These are eyeglasses with eye tracking software that collect data 100 times per second. They have four different sensors that measure your eye movement, and they measure gaze data as well as different eye movement states and events. For example, fixation, which is when your eyes are locked on one object, versus staycade, which is when your eyes are moving from target to target. And then we analyze this data in Tobii Pro Lab, which is a software that allows you to really take a closer look at the eye data that was collected from the glasses and tag certain areas of interest, times of interest, lots of different variables. More on that later. We then analyzed this data in Python, where we imported pandas, a useful data analysis library, as well as visualize this data. And this was very useful to sort of see our results. And then we also used Colab, which is a software that allows multiple people to work on code at the same time and have real time access to it. So our data acquisition process is shown below. This was a very interesting process because, again, as stated before, this is sort of a new way of looking at cyclist visibility and safety. So we're sort of trailblazers in this respect and had to start from ground zero essentially. So we created different experimental designs so that we could test for visibility. Then we actually implemented the data collection. We did it on two different occasions in person safely. And then after we collected all the data, we learned about the Tobii software capabilities and the different ways we could use the functionality. And then we determined exactly which functionality and variables we wanted to use to measure our visibility. And then we downloaded and tagged the data and imported it into Python. So this was our first data collection design. This was at the Pennovation Center. It was our sort of our initial trial. The driver was stationary in the car, and the helmet wearers rode on bikes. And you could see they came from different directions, as shown in the diagram laid out by the arrows. And on the right, you could see the different helmets that we used and the different directions that they came from. Um, this was this experiment was ran during the daytime and in a very controlled environment. We were in a parking lot that was essentially empty, so there were very few distractions, and this created a very safe environment. No one was hurt, obviously, and it was might have been at the expense of authenticity because this might not have been the most real life situation, but again, was very safe and a very helpful first data collection. Then we did a second data collection on the Schuylkill River Trail. We had a bicyclist wear the Tobii glasses and had different people wearing different helmets scattered throughout the Schuylkill River. And the bicyclist did not know where the people were going to be located or which helmets they were wearing. They were just driving down, and we wanted to see what caught their attention through the Tobii glasses. This was a real traffic situation with plenty of pedestrians and other cyclists on the path. So therefore, there were plenty of distractions, not to mention the physical condition of the fact that the biker had to also deal with staying on the bike, navigating, keeping their balance. So this was definitely a more realistic situation. Additionally, we did this data collection in the evening time, so natural visibility was already diminished versus what you would have during the day.
So as Brooke and Marlena said, we're kind of acting as trailblazers in this field of quantifying safety in terms of features that you can physically wear on you. And so our experimental design wasn't something that was intuitive. It was something that we really iterated through and designed together to try to make it like the best design possible to collect the data that we wanted. So our first experiment and data collection, as Marlena mentioned, was in the daytime in a very controlled environment. And so the iteration on that was we moved to the next trial and made it in the evening. So like Marlena said, natural visibility was a little bit compromised and more realistic environmental features were happening. Then also in the first experiment, our test subjects were aware of the experimental design. This was partly due to COVID restrictions, but the initial test subjects were us. And then when we did our second data collection on the Schuylkill, the test subjects went in blind. So they didn't know what exactly they were supposed to be looking for. And finally, in our first data collection, the glasses wearer was stationary behind a stop sign. And in the second, the glasses wearer was moving on a bicycle. So all these things, while they may seem obvious, were all parts of innovating on this experimental design to help create the most authentic experimental design possible when that's not something that currently exists or is in use. Another thing that we did that was an intentional design choice was the use of areas of interest in Tobii Pro Lab. So Tobii Pro Lab is the software that we used to import the videos and essentially tag the videos and annotate them before we export them into Python. Professor Ryerson and her team, for other experiments and data collections that they've done, typically use events of interest and times of interest, and then check gaze velocity and make gaze plot maps. So going into this project, that's what we figured that we would use. But after trying to do that and trying to measure the visibility of helmets, which is different than some of the other experiments, we realized that areas of interest would be the most useful. So basically what that means is we marked up the videos with little dynamically moving shapes. I know it's a little blurry, but on the right, you'll be able to see something that says color white, direction front, light, and time, night. So all that means is we have a small shape over on the right, and it's tagged with a bunch of features, meaning that that helmet there is white, we're looking at the front direction, the light is on, and the time of day is night. So I'm gonna play this video, and it shows a side-by-side of different views in Tobii Pro Lab. On the left, you can see someone's pupil movement, and as the circle gets larger, it means their pupil is fixating on something. And on the right, you'll see the different areas of interest that we tagged throughout different trials. So here, this was our Pennovation Center experiment. You can tell, oh no, it's loading. You can tell that it's daytime. And so you can see somebody's pupil following. That's Professor Ryerson on the bike. I think this is a really good measure, if you look on the left, of like a qualitative measure of actually how bright the Lumos helmet is. I know it's paused for a sec, but it's a far brighter measure, a far brighter light than any of the other pedestrians on the road. And it really sticks out. And then finally, this is also a Kickstart helmet, which is the one of the other Lumos helmets. Sorry, a little bit nauseating, but you can also see actually how bright it is compared to the other people and cyclists on the road. So our data analysis process had 5 overarching items that we wanted to take care of. The first was parameterizing a way to quantify safety. So as we've talked about a little bit in the past, safety is sort of this like qualitative, a little bit blurry measure that doesn't really have quantifiable parameters as of right now. So we wanted to think of this differently, and we thought of safety in terms of visibility, and that was something that we could parameterize a little bit more. So the 2 main parameters that we are working with here is number 1, time until first hit, which is basically the time that it takes for the person wearing the glasses to notice the helmet. and then percent hit, which is basically the percent of the time that the helmet is in view, that the person with the glasses is actually looking at the helmet. Next, we needed to determine which TOBY ProLab metrics to use. As we said before, TOBY has a bunch of different metrics such as gaze velocity, gaze plot maps, eye rotation, but we chose to use the area of interest hit or no hit metric. So a 0 if you're not hitting the area of interest and a 1 if you are, and also whether or not the eye is fixating or saccading, and also timestamps to measure the time until first hit. Next, we created a process to measure visibility. This basically looks like a Python script that takes in our data that we download from TOBY ProLab and outputs parameters such as time till first hit and percent hit. We can then compare visibility across different variables. So as I showed you in the video before, each of the helmets is tagged with color, time of day meaning day or night, light or no light. So all these things we can now compare these measures across, so we can tell time till first hit with lights versus without lights, and things like that. And then also planning for more data collection in the future. So already in this semester, we're planning to collect more data before we graduate, but also planning to make this a sustainable solution for people to collect more data and add to our methodology in the future.
Thank you, Jordan. In our analysis, we have found several important metrics that begin to answer some of the questions we initially set out to answer. So we discovered that Lumos helmets were noticed about 2.8 times more than regular helmets in our nighttime trials. We calculated this based on whether or not helmets were seen at all, and we found that many of the regular helmets were never even seen once. This tells us that lights really do improve visibility at night, which is a huge deal for nighttime commuters. Many people feel a bit more nervous riding at night, so being able to quantitatively improve their safety with lights will hopefully make people feel safer and prevent accidents. We also found that the Matrix helmet took about 1.6 times longer to notice than the Kickstart. We're a bit skeptical of this. Since the Matrix lights are brighter to the human eye, we were able to notice it first in tagging. So we were able to see it for longer, which could have skewed the data. However, if this ends up being validated by further trials, this fact would also contradict the increase in price from the Kickstart to the Matrix helmet. And finally, we found that in our data collections during the day, we did not see a clear, more visible helmet, and the Lumos helmet didn't show a significant impact on visibility when it was light out. So again, as we continue gathering more data, we may find a different result. We also had to account for several ethical concerns throughout the course of our project. First, as we mentioned earlier, the Lumos helmet is pretty expensive. So we don't want to imply that safety can only be achieved at such a high premium. But this seems to be part of a larger issue. We noticed that since there isn't a commonly accepted method used to truly quantify safety, there are very few companies who actually see this value in creating safety-oriented products, which might explain why Lumos decided to price their helmets so highly. This is another part of the reason we feel so strongly about this project, as we're hoping that quantifying safety can motivate helmet developers toward this goal. The second concern is the safety of the participants in our trials. So obviously, anytime we're putting people into real traffic situations, as we did in the Schuylkill River trials, always has the potential for danger. However, all of our participants were well informed about the experimental design and knew to be aware of other bikers and pedestrians on the river. And finally, it's really important that we present an honest analysis of our data to Lumos. So in order to stay true to our research and push the field forward, we need to make sure that we're not skewing our findings to favor Lumos in any way. our methodology and results can really help shape the future of cyclist safety in several domains. So we'll present our preliminary results to Lumos and continue to work with them to improve their technology and adjust their pricing strategy accordingly. Additionally, cyclists can hopefully use our findings to select a helmet to make them as visible as possible. And also, we're hoping that city planners and other institutions can build upon our framework and can also implement incentive programs to incentivize people to make safer helmet choices, similar to what we've seen done with electric cars. So as we've mentioned before, we'll be continuing to run additional trials through the end of the semester. This will allow us to gather a larger sample size of data and will therefore open up possibilities for new metrics we can analyze to quantify safety. We're really hoping that our methodology will be built upon by Dr. Ryerson's team and other researchers, and will ultimately help make roads safer. Working on this project has really made us realize how limited the current research about safety optimization is. And the method we created with our data collection and analysis can be used to examine a wide array of features that affect how visible someone on the road. And we're really excited to see how our framework helps inform the future of cyclist safety. Thank you.